I think no. Yeah.
No. Okay.
Or
maybe I quickly to introduce you, and then you can introduce you by yourself. Okay. So our next speaker is the Professor Jingwei Wang. Is from the Beijing Normal University in China, and today's his research is the expertise to study the membrane fouling mechanism. So today he bring a very interesting talk about the membrane fouling mitigation by particle fluidization. So please.
Okay. Thanks, Prof. Chang, for the introduce. My name is Jingwei Wang from the School of the Environment, Beijing Normal University. And for today, my presentation title is very short. It's membrane fouling mitigation by particle fluidization. It's a work one I've done in Singapore. Actually, my presenting background is related to the anaerobic membrane bioreactor. As we know, there have many advantages about the ANMBR, like the biogas production, high effluent quality, can feed with high concentration research targets. Includes the membrane fouling, removal efficiency, recovery. So our focus is membrane fouling. Also, there are many methods to control the fouling, like the innervation membrane materials, the membrane configuration, induce the chemicals. For today, I want to introduce is the physical method that we use the physical method because the physical method in MBR has been acknowledged as the most green and high efficient one. The methods include the typical like the cross flow rotation, the position flow, bubbling shear, vibration, and also the particle scoring, among which the particle fluidization has been regarded as the most energy efficient. Its function is like disturb the concentration polarization layer, sweep away the fallen particles from the membrane, and scour the cake layer. Can also generate the local turbulence. It was around 2011, Prof. Perry, Prof. Bay, and Prof. Kim, they proposed a novel purpose for wastewater treatment named anaerobic fluidized membrane bioreactor. So the technology is use the particle fluidization to control the membrane fouling in anaerobic membrane bioreactor. And they achieved promising results because the energy consumption is nearly to zero. At the same year, Prof. Perry also pointed out the potential of the wastewater. So he changed thinking, why could we change the wastewater treatment to the waste for the energy producer? Actually, the answer is yes, because we have the very low energy consumption fouling control method. Many papers have referred and compared the fouling control method in terms of the energy consumption. As you can see from the images, these figures, the particle scoring always achieved very low energy consumption, especially by couple with the submerged membrane module. So the energy consumption is very low. Actually, for the ANMBR, the membrane fouling control, especially in the industrial use, still use the bubbling shear method. Like we can recycle the biogas in the reactor, and then we induce the bubble to shear the membrane surface, like the common MBR, aerobic MBR. However, induce the bubble in the reactor accounts for very high energy consumption, around 50% of the total energy for the wastewater treatment. By using the particle scoring, there has many advantages, like reduce the bubble amount, high fouling control property, very easy for the application, but with very low energy cost. This figure shows the typical FBR like that we can put the particles in the reactor. Then we use the fluid to recycle and make the particle to fluidize. And by using this method, we can control the falling well, but can eliminate the induced of the gas, so the energy consumption is low. This photo I captured in my previous work, that we can put the millimeter-sized granular activated carbon in the reactor. Then we use the water to make it fluidized. Yeah, just use the water recirculation to make it fluidized. Then we can put the flat sheet or the hollow fiber membrane module and submerge it in the fluidized bed. Then we can control the falling. Because the particle scoring holds the key for the membrane falling mitigation, then today I want to introduce in two aspects. One is efficiency. Another is hydrodynamic scoring efficiency while accelerometer sensor. We can imagine if we want to use the larger particles to make it fluidized, then we must put more energy. So first we determine the minimum fluidization velocity. It's the liquid velocity that the particle just start to fluidize. We can use the very simple method, the pressure drop, to determine it. As we can see that with decreasing the particle size, UMF also decreased, means low energy consumption. So our question is, at the same energy consumption, maybe the larger size or the smaller size is better for the falling mitigation. To solve this problem, then we use accelerometer sensor. It's a non-invasive probe. We can attach it outside the wall of the reactor, then not disturb the fluidization. The process is like this. The particle fluidization, then we attach the accelerometer sensor outside the wall. And then we can use the data logging card and also LabVIEW to log the signals. The raw accelerometer signals is like this in the right image. Okay, then to interpret the signals, then we use the MATLAB and the method wavelet decomposition to analyze the signals. The process is like this. The raw signal is split into several subsignals with different frequencies. So the working is like this one. The raw signal split into the subsignals. And finally, we use the typical wave energy equation. Then we can transfer the raw signals into the very beautiful curve. Yeah, it's like this one. Because the accelerometer sensor captures the shear, includes the liquid and also the solid. So the first thing is to split them. We compare the accelerometer signal and under different fluidization situation. Like the first image, if there's without GEC fluidization, only one peak showed in the curve. If we start the fluidization at especially different size of GEC, then we can see there appeared two significant peaks. So we can know that the first peak refer to the GEC shear, and the second one is responsible for the liquid. By using this method, we can quantitatively measure the particle scoring efficiency at different superficial liquid velocity. Like if the cross flow velocity over the UMF, there shows signals. Also, at the same liquid velocity, larger particles achieved higher particle scoring. This figure shows the falling test and the UMF value. As you can see that without the GEC fluidization, the TMP increased very fast, but with the scoring of the fluidized GEC is very slow. So we can know that from the investigation, we can know that the key to enhance the particle scoring efficiency for a particle balanced by the measure like this highlighted image. At the same energy consumption, we compared the scoring efficiency for different size GEC. We found that at the same energy consumption, the larger particle enhanced the scoring efficiency is around 50% higher than the smaller one. So it's very interesting to use the large particles. We also further put the accelerometer sensor in the pilot scale FMBRs. This is the pilot scale accelerometer sensor for the troubleshooting. Then we can actually know the detailed location and which part have the problem. Okay, then we go to the next part, characterizing the particle fluidization hydrodynamics. For this section, we use a typical rectangular reactor, FMBR reactor. Because it's transparent, then at the fluidization situation, it's lab scale reactor. The dimension is like this. So we can use a high-speed camera to capture the motion of fluidized GC. The captured image is like this. The image A and image B are 0.01 second time apart. Then we can give each GC particle coordinate. And use these coordinates, we can calculate the particle velocity, particle concentration, particle momentum like this, and also the particle and also the energy consumption. We measure, we calculate large amount of the data, then we use statistical analysis to analyze the data. This figure shows the probability of the particle velocity. At different height of membrane, we also compare the size. As you can see, this distribution, that lower part had broader distribution. OVP means that at the lower part, the fluidized GC can achieve higher particle velocity. The higher part of the membrane can cause very evenly distribution and also a little lower particle velocity. We finally use the RMS method to calculate the mean. This figure shows the detail. You can see that at the same overall GC concentration, like we put 90 grams per liter overall GC concentration, the larger particle can achieve a little higher particle velocity, but the smaller particle can achieve a little higher local particle concentration. It's very interesting to analyze the particle momentum because we know the fluidization is the phenomenon that the momentum transfer from the liquid to the solid. So we can see from the results very clear that the larger particles achieve very high particle momentum compared to the smaller one. We also do the folding test at the different part of the membrane. As mentioned previously, the lower part had broader distribution, means higher particle velocity. And also the folding test showed that the lower part had a higher folding mitigation performance. And also, we compared different sides. The larger particle also better than the smaller one. Finally, we correlate all the particle hydrodynamics parameter to the membrane folding to the folding increase rate. We found that if we increase the particle hydrodynamics, typically it will help us to control the membrane folding. There showed strong correlation between the particle momentum and also the membrane folding rate. Means that the momentum transfer holds the key for the particle fluidization. Okay, finally, short summary. For the results I introduced are the main findings. One is at the same energy consumption, larger particles had higher scoring efficacy. The second is the mechanism. The key to control the membrane folding is the particle momentum for the particle fluidization technology. And also for the pellet scale, we can find that the particle fluidization situation is not good. So the membrane configuration is still important for the pellet scale reactor. In the future, we design the AFMBR reactor towards the high particle momentum. We also have some future tasks. It may decrease the membrane damage issue, like as mentioned, the lower part had higher membrane folding control property, but also damaged the membrane. And also the inline monitor system is very important for the pellet scale reactor, like to monitor the diffractation and also the particle clogging issue like this. And also enhance the methane production is important as the key target is to achieve the zero energy consumption for wastewater treatment. So the low energy consumption for the folding mitigation plus the high biogas production will toward our target. We also have several publications related to this research field. Okay, finally, sincerely thank to Prof. Chu Jiawei, Prof. Tony Feng, and Prof. Liu Yu from the Nanyang Technological University, and also Prof. Wu Bin, now in University of Iceland. Thanks the funding from PUB and also my previous workplace, SMTC. Okay.
The internet has a little bit delay. Could you hear me? Professor Wang?
Yeah, I'm here.
You can hear me?
Yeah, I can hear.
Okay. Thanks for your thanks for your wonderful talk and now we are opening some questions from the audience. Okay, so please write a message if you have the questions. Any questions? Okay, maybe I will ask first. In your study, I think it's good to let the fluidization of the you use the GAC particle, right?
Yeah, correct.
GAC particle is a promising method to reduce the membrane fouling, like you said, especially in the membrane bioreactor. It has been received extensive attention. But in your research, have you found that in the fluid dynamic analysis of the GAC particle, is there any critical liquid velocity that will optimize the and effective control energy consumption of the membrane fouling?
Okay, good question. Actually, from our research, we found one issue that for each size of the particles, they have the energy input boundary. Like the smaller particle, we can input just this narrow range of the energy. Then for the larger particle, we can use very a little higher liquid velocity to input more energy. Actually, if folding mitigation, but we have the max boundary for this.
I see. Okay, I see. So any other question from audience? Please write in message if you want. Okay, if no, I will close the talk in this session, and let us to thank the Professor Wang again.
Thank you.
Okay, so our next speaker. So we'll handle the next speaker first. Okay, Professor Wang.
Okay, sure. Then
okay.
Okay.
And you will introduce the final one in this session. Okay.
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 Then I introduce the next speaker. It's Hussein Abilgazim, from the chair of Mechanical Process Engineering and Water Technology, University of Duisburg in Germany. Following behavior of layer modified nanofiltration, happily reception performance. Then welcome Hussein to start the presentation.
Yep. Really thanks for the warm introduction. So I'm Hussein Abilgazim, and today I would like to share my results for the results I obtained from my PhD ongoing PhD study. So my presentation topic will be studying the fouling behavior of layer by layer modified nanofiltration capillary membranes in water treatment and its impact on the separation performance. I do my PhD, those are the co-authors in this study, and I do my PhD under the supervision of Professor Stefan Panglish, as already said, in the University of Duisburg. So the scope of the work will be that we wanted to study the visibility of a new capillary NF membranes for drinking water treatment applications. Also, we wanted to test the impacts of the operating conditions on the fouling propensity in addition to salts and organics retention. We wanted to see these operating conditions in a performance in cross-flow and in a dead-end operation modes. Also, we wanted to investigate the different mechanical cleaning techniques for heavily fouled capillary nanofiltration membranes. So, to perform these fouling experiments, a synthetic model feed water, which is mimicking the surface water in Germany, has been introduced. This modeling water will be used by the potting soil extract, which is a typical fouling surrogate for UF membranes that will be used as a source of natural organic matter substances. To perform the potting soil extract that we will use to make a dilution or to mimic our surface water, we need also to reach a surface water condition in terms of the conductivity of around 500 microsiemens per centimeter. That's why we added also to our potting soil extract a reef salt at a concentration of 300 milligrams per liter. So the membrane specification of these newly modified layer by layer nanofiltration capillary membranes is based on a modified multipore, let's say Inge membrane, which is like a daughter company of DuPont. So we have the multipore, or let's say the conventional UF membrane, and then we started to coat it. The coating or the fabrication using the layer by layer is actually in terms of using a polycation, which is the PDA-DMC, and also the polyanion, which is the PSS. This is the polydiallyl dimethyl ammonium chloride, and the polyanion is the polystyrene sulfonate. And as I said, it's based on a support layer, which is actually the UF, which is based from polyether sulfone. The molecular weight cutoff of the new capillary nanofiltration membranes, or let's say the modified multipore membrane, having a molecular weight of 400 Dalton measured using PEG, or the polyethylene glycol. The module has a length of 30 centimeters and have an active surface area of 0.05 meters square. The zeta potential measured for this modified multipore has a value of minus 40 millivolt at a pH of 7. The pure water permeability of this membrane has a 10 LMH per bar and has a magnesium sulfate retention of 85. So the magnesium sulfate, or let's say this retention, has been calculated based on this test condition, that 600 milligram magnesium sulfate at a cross-flow mode or cross-flow velocity of 0.22 meters per second and a constant pressure of 2.5 bar and a temperature of 25 degrees Celsius. So before I go further and show the results, I want only to give like a short overview. What is the concept of the layer by layer? So actually, you have a support layer, or let's say a porous membrane, which in this case, as I said, is the multipore Enge membrane, which is the UF membrane, which has mainly, let's say, in a range of molecular weight cutoff of 80 to 100 kilodalton. And then you fabricate from the UF, or let's say the support layer, with the fabrication, or let's say coating with polyelectrolytes, which is in the beginning the polycation, the positive one, and then you will have your layer that has been formed above the support layer of the UF. And then you apply the polyanion, which, as I said, is the PSS. Then you have one set of two polyelectrolyte layers, which is called in these terms one double layer or bilayer. And you repeated this method several times until you formed your layer by layer, or let's say in this case, we called it polyelectrolyte coated membrane, which is made in a range of 400 to 800. The one that we have it here, the modified multipore, has a molecular weight cutoff of 400 dalton. So this is a cross-section area of these multipore modified Enge membranes. So we start now with the results of the synthetic model water components that we use, as I said, and then the synthetic model water is mainly, as I said, the potting soil, which has a liquid chromatography organic carbon detection analysis, which shows a chemical composition of the potting soil used for these experiments at the TOC value that ranges from 5 to 30 milligram per liter. This mainly the potting soil that we have, I mean the original stock solution, is mainly a humic acid substance, which represents almost 66%. There is in this potting soil extract as a source of natural organic matter, building blocks as a representative of the humic acid substances, also biopolymers as the polysaccharides, also low molecular weight and neutrals, and acids. And there is no any hydrophobic organic carbon. So, as I said, to simulate the surface water and to have a conductivity of almost 500 microsiemens, we added a reef salt in a concentration of 300 milligram, in which the reef salt, or let's say the commercial reef salt, is mainly having these components, the sodium, which is mainly sodium chloride. That's why you will see that the values of the sodium is 76 milligram per liter and the chloride is 146. So the experiments that I have performed to check the visibility of these nanofiltration capillary membranes, or modified layer by layer, I use the different initial feed compositions. So to simplify it, we use the 3 different initial feed concentrations with Cl as a low value, which corresponds to a TOC of 5, and we add a reef salt of 300 milligram, or a medium concentration, that's why we call it Cl, with 17 milligram per liter TOC, and also 1000 milligram, or let's say 1 gram of reef salt. And then a high concentration is 29 milligram per liter, and the reef salt. The experiments have been done as an patch experiments, were performed with an automated mini plant membrane provided by the Convergence from Netherlands. So the results here will be that the influence of the initial feed concentration on the membrane performance can be simulated. That is, as I said, in the patch experiments, in which we run a filtration of 3 hours. We recirculate both the retentate and the permeate, and in the y-axis you will see the normalized permeability. When we tested the low concentration and the medium and also the high. This synthetic model water, as I said, has a pH of 7.5, and we run it in a constant flux of 30 LMH in a cross flow velocity of 0.3 meter per second, as I said, for 3 hours. And those are the compositions again from the former slide, so that you could follow up what they mean by the Cl, the low and the medium and the high. As you could see from the results, a very limited permeability decline has been observed under these operating conditions, even at the initial feed concentration with the higher values, in which the decline can be summarized that in the case of the low and in the medium, the decline in the permeability is mainly in a range of 5%. Even in the higher 29 TOC value, it's only 7%. So also we check the influence of the initial feed concentration on the membrane retention. Here in these terms, again, we use the low, the medium, and the high initial feed concentration. And we measure the retention in terms of organics, which is measured in TOC and UV 254 nanometer, and also in turbidity. And as you could see that whenever we increase the initial feed concentration, the increase in the retention of the organics has been detected. As you could see, mainly, for example, in the case of the TOC, in which the lower was in range of 95%. However, whenever we increase the initial concentration, a higher retention has been observed. In the terms also, if we see the salts, that the retention here of the salts measured in terms of conductivity, that it's mainly because, as I said, because of sodium chloride. So that's why the retention is mainly 20%. Also, when we go deeper and see the cations, I mean the monovalent in terms of sodium and potassium, we know that the retention is in the range of 10% in these conditions. The retention of the divalents in the case of magnesium and calcium, a retention has been as we increase the initial feed concentration, I mean the chloride mainly because of sodium chloride, that means there is a decrease of the retention of the magnesium and calcium if we compare these values. That instead of starting from 70%, we end up with 60% whenever we increase the initial feed concentration. The sulfate shows in all the conditions a 98%. However, we increase it the initial concentration. Okay, so also we wanted to test the influence of the filtration flux on the membrane performance. That's why we repeated the same experiment. However, we took only a constant initial feed concentration. That's why we used the medium feed concentration, it's TOCl17, and a result of 1000. Whenever we increase the fluxes from 15, 30, and 45, that is the blue one, the 15, the green one, and the orange. Whenever we increase the flux, a stable membrane performance was seen in 15 and in 30 LMH. However, a relative stronger fouling in 45 LMH has been seen, which is mainly in terms of, let's say, 9% membrane decline. So the influence of the filtration flux on the membrane retention has also been studied, again, in terms of organics and also in terms of the salt. As you could see here, in the terms of the organics, again, a retention of the organics was mainly in all the terms of TOC or UV or turbidity in a range of 96%. However, the retention of the salts here, as we know, the increasing of the higher fluxes, for example, if we focus here in the magnesium mainly, and the calcium, you would see that whenever you increase the fluxes, in the high fluxes, the increase in the salt retention is mainly solution diffusion model, or let's say the diffusion effect. So that's let's say concluded that the retention is mainly dominated by charge exclusion, let's say rather than size exclusion. Even in the cases here of different fluxes, again, the sulfate shows 98% retention. The chloride is again around 10%. Again, we wanted to test the operation conditions, so we increased the cross-flow. Let's say we tested two different cross-flow velocities with different initial feed concentration as the same method. As you could see, the green one is the 0.3 meters per second, and the orange one is the 0.6. So we tested two different cross-flow velocities at a constant flux of 50 LMH, and we could see that the retention, or let's say the decline in the permeability, is as we increase the cross-flow velocity or increase the shear force, so a lower permeability decline can be observed, which can be easily seen here, that here almost 30% in the case of the high initial feed concentration, which is 15% only in 0.6. The retention also has been measured with these different cross-flow velocities and different initial feed concentration, again measured in terms of organics and salts. As you could see, whenever we use the initial feed concentration as a low value or a medium value or even a high, no significant influence of the cross-flow velocity applied on the 0.3 or the 0.6 has been observed. The organics also, again, in the same condition, 95%. The salt was mainly 12%, that is sodium chloride mainly, the result, and the sulfate is 97%. Here we wanted to see the performance of the capillary membrane when we perform it for a longer time. So instead of running it in a cross-flow mode for only 3 hours, we prolonged the experiment for 9 hours. So 3 consecutive filtration cycles. After each cycle, we perform a backwashing in which the backwashing has been run for 70 LMH for 90 seconds. As you could see, after the 9 hours, a decline of almost 20% in the permeability has been observed. Also, we wanted to test, is it possible for these capillary nanofiltration membranes to run it in a dead-end mode? That's why we run 6 consecutive cycles, in which either after each 1 hour we apply backwashing at 70 at the same condition before, or we forward flush it at 0.6 meter per second. Here in this case, as I said, it's dead-end mode. That's why we run it in a flux of 35 LMH. And as I said, after 1 hour, we applied either a backwash or we applied a forward flushing. The backwash, as the polyelectrolyte layer, we need to maintain its mechanical stability. That's why only after 3 hours we reach like the maximum applied pressure for backwashing. However, in the forward flush, we could perform more cycles. The retention in the dead end, as you could see, that the retention here measured in terms of the organics in the TOC or also in the UV 254, that when we measure the retention in terms of the first cycles out of the 6, and because in the backwash only 3 cycles has been performed, you could see that when we collected the samples only at the last 10 minutes of each 1 hour of filtration, we see that the TOC is lower, which is 85 in comparison to the cross-flow modes, which is 95, or let's say minimum 95%. UV is again higher than this one. However, the salt is again lower than the 15%, which is mainly due to, in comparison to cross-flow velocity to concentration polarization effect. So to sum it up, the conclusion that we have that the layer by layer modified capillary nanofiltration membranes showed the promising performance in both cross-flow and dead end. However, the dead end, due to the concentration polarization, more experiments should be maintained. The high retention ability for the dissolved organic substance, along with acceptable divalent cations removal or softening, in which is a potential application in drinking water treatment. Higher sulfate retention at all operating conditions, and the performance recovery was mainly with a simple chemical cleaning. The outlook, what we will do is that adaptation of mechanical cleaning techniques with less chemical cleaning frequency, and also testing of different operation modes like feed and bleed, not like a typical dead end mode, and also the selective retention of certain organic substances, for example, algae, and so on. The acknowledgement, I would like to acknowledge the Heinrich Böll Foundation for funding me or supporting me during these PhD studies. So if you have any questions, you can contact me using this email address. Thanks.
Thank you, Hussein. Very nice results. Anyone have the questions? Can write. I have just a short question. Did you test the membrane morphology like use SEM or AFM for the chemical cleaning? Because you mentioned that for your membrane, you can remove some salts. Also, to recover the membrane, maybe we need to use like the sodium hypochlorite or the acid and base to clean the membrane. How the membrane property after the cleaning?
Yeah, this is really a good question. Yeah, after each filtration cycle, let's assume here in the results that I have shown, whenever we perform an experiment, after we see the decline, let's say, assume in this case it's 20%, then we see the stability, the chemical stability of the polyelectrolyte layer. That's why we tested it in the sulfuric acid at a pH of 1.5. And also we tested stability in the sodium hypochlorite in a range of 50 to 200 ppm and a pH range of 10 to 12. And it was stable and we could restore it easily.
Okay, thank you. Anyone have other question? Okay, if no question, then we go to the next.
Okay, and Misty, can you hear me? Could you upload your slide? Please test your voice.
Prof. Zhang, can you see the slides?
Wait.
Is this okay?
Yes, good. Okay, good. Okay, so let me introduce the next speaker. It's the Miss Tian Li. It's from the Tongji University in China. So today she will present the topic about the simulating the critical roles of zeta potential and content angle on colloidal fouling of NF membranes. Please.
Thanks, Prof. Zhang, for the introduction. I'm Li Tian from Tongji University. So today's my presentation will include the 4 parts. First, I will give an introduction on the NF membrane in the water treatment, especially in drinking water treatment for the high quality water production, following by our experimental study of dissolved organic matter on nanofiltration membrane folding and folding mechanism. We also have done some simulation work of the dissolved organic matter on NF folding and the folding mechanism. Finally, I will end my presentation with conclusions and acknowledgement. The nanofiltration are widely used in water purification technology. With the increase of the economy development, to produce the nanofiltration can be also combined with the conventional water treatment and the ozone-layer biological activated carbon for further purification technologies. And filtration. In the past few years, the nanofiltration membrane folding can be characterized by the XDLVO theory. The XDLVO theory describes the energy between the total energy interaction of the 3 parts. One is the van der Waals interaction, and the second is the acid-base interaction, and the third one is the electrostatic interaction. And the total interaction energy can be determined by the three parts. And when the separation distance is very small, the interaction energy is negative, and that means the attraction force. And when the separation increases, the force becomes the repel force. So the force is the repel force. In the conventional concentration polarization model, the model shows that the diffusion, the water and the solutes pass through the membrane, and some of the solutes was rejected, and also some was diffusion. And in our model, we add the part for the collision. Thus, by solving the mass mass boundary equation, we can solve the relationship between the concentrations of the feed, the concentration of the membrane, and also the diffusion part. And in this part, we improve the conventional concentration relation model, and we increase the Pecnik number, which is the ratio of the convection transport over the diffusion transport, and can be used for our condition model. And in our model, we also include the attachment model, which is proportional to the which describes that the folding rate is proportional to the specific particle resistance times the flux and also the back concentration, and combined with the attachment, we can use to model the relationship between the attachment and also the energy barrier. So in our experimental study, we include NF-TM610 membrane, and we also use the BSA molecules for the influent. And this is our experimental setup. Let's see some experimental results first. We first measure the data potential of the BSA molecules. And we find that the ISA point of the BSA is around 4.7, and below 4.7, the data potential of the BSA is greatly dependent on the ionic strength. With a lower ionic strength of 1 millimole, the data potential first decreased. Then around 4.7, it becomes nearly 0, and when the pH further increased, the data potential becomes larger for the reactive value. And since the data potential of the BSA value is around 4.7, so we find that the water flux of when the pH is around 4, the water flux drops significantly, while for the pH of 7 and 10, the water flux drops slightly. And we measure the water flux of the water with different ionic strengths of calcium concentration with 1 millimole, 10 millimole, and 100 millimole for different pH. And we find that at the low ionic strength, the water flux, for example, at around 4, the water flux is high, but for example, at the 1 millimole ionic strength, the water flux is high. However, it decreased significantly. And comparing with the different change of the water flux of different pH and the ionic strength, we find that with the increase of ionic strength, the water flux reduces, but it's relatively stable. And with all this water flux, the pH of around 4 is the smallest, which was probably due to that at pH of 4, the ISA point is very close to the 4.7. For the modeling work, for the thorough analysis, we use the XDLVO interaction energy to characterize the folding mechanism. We measure the 3 interaction energies, and we also measure the total interaction energies. And we find that at the pH of 4, the total energy is negative, which means that the chlorides tend to aggregate. And when the pH increases, the total energy becomes positive. That means that the repulsion force is dominated, that the membrane folding can be reduced. Comparing with the higher ionic strength and the lower ionic strength of 100 millimole and 10 millimole, we find that the interaction of the higher ionic strength of 100 mole, the interaction energy is smaller than that of the lower ionic strength. That the membrane folding with the higher ionic strength is higher than that of the lower ionic strength. And with all this interaction energy calculation, we find that the membrane folding is first determined by the membrane phonon interaction, then determined by the phonon interaction. Then let's go to our modeling work. We first model the different pH of the interaction energy. We similar as that of the experimental work, we found that with the increase of pH, the increment of the elective zeta potential of both the phonon and the phonon membrane increased, and also the water content angle decreased. And with the when the pH is at the ISO point, significantly membrane induced, which may be due to the absence of the energy barrier. Let's see the zeta potential on the attachment efficiency and the membrane folding rate. We find that with a lower attachment, with a lower zeta potential score and a higher flux, the permeate drag induces effective collision and successful phonon attachment. Thus, can be result to the collision dominated. While with the increase of the zeta potential score or lower the flux, there is a dramatic drop of the folding rate. Thus, the attachment can be dominated. Let's see the zeta potential on the membrane folding rate and the water permeate flux. From the first figure, we can see that when the zeta potential increase from 10 square to 50 square, the water flux increases significantly, and from 20 to 30, there is a very big drop. Thus, we can see that increase the zeta potential score can substantially induce the elevation of the membrane folding. And from the right-hand side figure, we can see that with the increase of the zeta potential score, the energy barrier increased proportionally. Thus, the elevation of the membrane folding can be directly related to the energy barrier change. And from this, we can also see that with the enhanced membrane phonon electron repulsion, the folding by the elective charge colloids tend to be mild with the high pH and low ionic stress, thus also the calcium concentration. Since the contact angle is related to the electrostatic interaction, thus we also simulate the contact angle on the attachment efficiency and the membrane folding rate. From the left-hand side result, we can see that with the increase of the contact angle and the attachment efficiency also increased, and with the increase of the water flux, the attachment efficiency also increased. While on the right-hand side, we can see that with the increase of the contact angle, the folding rate also increased. Thus, we can see that lower the flux or contact angle can result to the increased attachment. Then we also simulate the contact angle on the energy barrier and the water permeate flux. From the left-hand side, we can see that when the contact angle decreased, the water flux decreased significantly, and on the right-hand side, it also shows that when we increase the contact angle, the energy barrier, there is a very significant transition. First decrease very fast, then decrease slowly. Thus, we confirm that there is a critical contact angle which can influence the membrane folding due to the quickly increasing energy barrier. And at the low contact angle, the phonon and the membrane surface generally have low hydrophobicity that decrease the contact angle to result in the enhancement of the hydrophilicity and repulsive AB interaction energy, and thus the elevation of the membrane folding. And to summarize, we can see that the relationship between the zeta potential, contact angle, and the critical flux. And we can see that as more critical flux is observed at a lower zeta potential square or higher contact angle, owing to the small repulsion of the phonon membrane. While further increasing the zeta potential square or decreasing the contact angle can lead to a rapid increasing critical flux corresponding to the rapid increased energy barrier, and thus decrease the attachment efficiency by orders of magnitude. With all this, I want to conclude that we confirm the importance of the zeta potential and contact angle on the energy barrier and the folding rate. At a lower zeta potential square, severe folding occurs due to the lack of energy barrier, and increase the zeta potential square can substantially reduce the folding as a result of the linear increasing energy barrier. A critical contact angle relating to the folding exists, owing to the dramatically increasing energy barrier and thus decreasing the folding rate by orders of magnitude. And we can also see that the threshold contact angle appear at the AB interaction energy altering from the negative to the positive, for example, from the attraction to repulsion. Finally, I want to take this opportunity to thank the funding agency of the major science and technology program for water pollution control and treatment, and also the National Natural Science Foundation of China and the National Science Foundation of Shanghai. And I would like to also thank my colleagues and my collaborations of Prof. Liu Junxia, Prof. Dong Bingzi, and Prof. Tang Chuyang. And finally, I want to share with you about a special issue on the yellow water. It's about the new advanced oxidation processes and catalysts for water and wastewater treatment. And the submission deadline first was on November 20. However, it will be extended. So anyone who are doing the AOP and catalyst, you can still submit this special issue. And thank you for all your attention.
Okay, so we thanks the Ms. Li presentation, nice talk. So now is the time to open just one questions from the audience. If you have any question, you can write the your question in the website.
Yes. And this asks for the interaction energy analysis. Do you measure the energy component of XDLVO equation or just estimate from it? We measure we measure the contact angles, and then we calculate the energy interactions. So with all these equations, and also some other equations that were not listed here, we measure this is the zeta potential. Then we measure the zeta potential and the contact angle, and we calculate. We not estimate by citing from other references.
Okay, thank you. And the other questions? If no, I have one, is that this is very meaningful research work using the calculation, and we know that the to prevent the membrane fouling, it's quite important to control the surface hydrophilicity, also their potentials. So do you find any from the many studies that show that the zero potential should be approached to zero, and of course content go as low as possible to prevent falling, right? So based on your study, is that possible to really find the zero potential study window to show this mechanism, anti-fouling mechanism?
Hello, Prof. Zhang.
Yeah.
I think you may have some misunderstanding. We think that when the zeta potential is near zero, the energy barrier is very, it is near the ISO point. Then the energy barrier is negative or not very stable. So is the attraction force. That means that the photon can be attracted on the membrane, so it will lead to the high Fourier rate. So we don't want to work at the isoelectrical point.
I see. So just one suggestion is that if possible, then maybe you can also check the membrane itself, like the membrane's zeta potential maybe is also important factor.
Yes. The membrane contact angle and zeta potential also, I think they are correlated.
Okay.
They both can, they both can affect the membrane folding and the membrane filtration performance.
I see. Okay, thank you. Thanks for your talk. Let us to thanks the Dr. Lee again. Thank you. So today we will today we will close the session in just 4 talks. And thanks Professor Wang host the session. And Professor, do you want to say something? Hello?
I just want to thank you.
It's okay, Prof. Zhang. Yeah.
Okay.
Thank you.
Yeah.
Oh, thank you.
Yeah, thanks everyone to join this session, and hope you can also join other interesting topic. Okay.
Yeah, really thanks.
Yeah.
Really thank you.
Bye.
Thank you. Bye bye.
Yeah,
Bye.
bye. Have a nice day.